Hi everyone, Martin here, welcome to the Inner Loop. In this episode of the PicoDrone, we're going to finish this top. We're going to finish this top row. We're going to talk about everything. We're going to get that finished. So we should have talked about the output stage, D2A, the delay looper, and all that stuff. And hopefully covered a lot of the hardware as well. I wanted to talk a little bit about resistors. What happens if we have two resistors? R1 and R2, and they're in series. What is the resistance? R3. So what does that resistance equal? We know there's a voltage across here, V. And we know there's a current I through here. And we know the current I goes all the way around. These two are in series, so their current is the same all the way around. So that would be the same as I through R3. So we know V equals IR. So V equals, that's this total voltage, equals I times R3. That's what we're after. We know here there's a voltage V1 and V2, and we know that V1 plus V2 equals V, that way. Well, V1 is I times R1. So I times R1 plus I times R2 equals V. Now we can equate these two together. I times R1 plus I times R2 equals I times R3. Get rid of the I, divide by I all the way through, it disappears. So R3 equals R1 plus R2. So when we have resistors in series, their equivalent value is just the sum of their values. This is a bit of mental warm-up. Let's have a look at resistors in parallel, because that might be more confusing. We have some voltage here, V. We have R1. We have R2. And they're going to be equivalent to something that we're going to call R3. In parallel, we know that they all have the same voltage across them. We also know there's a current I flowing here, so that current I would be going through our single resistor R3. But the current here is going to split. It's going to go a bit through this resistor and a bit through that resistor. So let's call this I1 and I2. So what we want to get rid of is the V term and use we know that I equals I1 plus I2, because we know that none of the current can get lost. But we can work out R3 in terms of V. It says V equals IR. So the current I is V divided by R. So here we have V divided by R3. Here the currents are going to disappear. Equals RV divided by R1 plus V divided by R2. I'm just watching this video back before I post it, and I've realised that I made a complete mess of that. We got to this point where we had V divided by R3 equals V divided by R1 plus V divided by R2. And what I was about to do was to start finding the lowest common denominator and multiplying this all out. But it's completely unnecessary. We just need to divide everything by V, and we get 1 over R3 equals 1 over R1 plus 1 over R2. So R3 equals 1 over R1 plus 1 over R2. But what I did get from that is a very useful another way of visualizing that, which is you can actually have R3 equal to R1 times R2 divided by R1 plus R2. Okay, I'm sorry for all that mathematics, but let's look at a circuit diagram. And these are either going to be plus 1 volt or naught. It can be one or the other, plus 1 volt or naught. So 1 or naught, 1 or naught, 1 or naught. Naught's here, 1 we don't see. If we make this resistor 1 ohm, this one 2, this one 4, and this one 8, what's the voltage going to be here if these are all naught? Then that's going to be naught. So we can do a little truth table. So let's call these points 8, 4, 2, 1. So if the resistor 8 is naught, resistor 4 is naught, resistor 2 is naught, and resistor 1 is naught, it's naught. There's no choice. What would happen if we made resistor 1 1? So we're going to connect resistor 1, which is 1 ohms, to 1 volt. So this is 1 volt, this is 0, 0, 0. This gives a circuit diagram that looks like this. So what's the voltage V at this point? So we can do our resistor mathematics here. This resistance 1 ohm. This resistance is 1 over 2 plus 1 over 4 plus 1 over 8, 1 over all of that. 0.875 equals 1.142857 bar. So what would the voltage be here? There's a 1 ohm there and a 1.14 ohm there. So the total resistance R would be 2.1428. So that actually comes to 0.533 reoccurring. So that's 0.5 of 533 volts. What happens if we maybe put this one also? So the 2 ohm, so we've got a new circuit now. We've got a 1 ohm and a 2 ohm against a 4 and an 8. So we'll have to do the maths again. Eight plus the 2 divided by 10 thirds, which is very nice. It's 8/10 of a volt, which is 0.8. I guess you see where that was heading. It was going to become a lot of maths. So what I've done is convert this to a spreadsheet. You can see with 4 resistors, you can see where this is heading. We're actually making a 4-bit digital to analog converter. So here's our decimal value with 4 bits, which is 0 to 15. Here's the binary equivalence, 0, 0, 0, etc. The highest bit is the 1 ohm resistor. Next bit down is 2, 4 and 8. So the 8 ohm resistor, which is the largest one, is going to have the smallest effect on the voltage, so I reckon that's going to be the least significant bit. What I've done then is I've calculated the resistance based on whether the bit is high or low. R1 is the high bit, so which has been pulled up to 1 volt, and R0 is the remaining resistance, which goes to 0. So in the case where we've got 8 ohms to 1 volt, R1 is 8, and the rest is the combination of 1 ohm, 2 ohms and 4 ohms, which is 0.57. And then the voltage that creates is then calculated here. If all the resistors are to 0, then it's 0. If all the resistors are to 1, then it's 1. Doubling the resistor each time or halving the resistor each time might work with binary and analog voltage, but it's not obvious. So this is how this turns out. So let's look at a graph of it and see if it really does work. I was really excited when I saw this graph for the first time, because along the bottom here we have our decimal value, which then becomes the binary value and sets which resistor is at what. And then horizontally here we have the voltage. And it's a perfect linear graph. So using resistors that double in value works precisely to create a digital to analog converter. Here we are on the Pico. I got one of those development boards, and all I've done is added 14 resistors, actually pairs of resistors, to try and get to the right values that double in value. So it's 50 ohms, 100 ohms, etc. all the way down. I figured a 14-bit D2A would make quite a good sound. So there it is, digital to analog converter. Let's have a look at the code and how we communicate with that. I think the reason I chose this approach was, once you've got the right resistor values, within the code, all I need to do is call a function called D2A and send in a value. And the value can be from 0 to 16384, which gives us our 14-bit number, which can range from 0 to 16384. I actually add on 8192 because the number that I'm sending in varies between plus and minus 8192. Crikey, Martin, there's a huge bug in your code there, because you've declared the incoming variable as an unsigned int, yet it's going to be signed, it's going to be plus or minus. I seriously need to fix that. In fact, I'm surprised the PicoDrone works at all like that. When we get to the D2A, we need to have a value from 0 to 16384. What happens here is GPI puts a value onto a pin on the Pico. Pin 0 is where we've got the 50 ohm resistor, and it's like that most significant bit, so we AND it with 8192. Then we just go down, ANDing with the increasingly smaller values until pin 13 we AND it with 1, so the last bit is either 1 or 0. And that's how the D2A works in terms of coding. All I have to do is call this function D2A with a value, and that will create that voltage value that we want. A little look at the final circuit diagram. So these are our resistors that you saw. They go from 50 ohms, 100, 200, 400, 800, 1.6K, all the way down to 409.6K, which gives us our 14 bits. They all join to a single point, which goes into the plus of op-amp. It's a TLV 2462. It's a Texas rail-to-rail op-amp. There's also on that board a voltage regulator, an HT7333. That's a 3.3 volt regulator. So that takes some of the load off the Raspberry Pi, so that can power the op-amp and also send voltage to the 3 pots that are needed for the analog to digital part. The outputs, this is the output stage. The output from the op-amp then goes to a 10K variable resistor, which basically is used for volume, and a 0.1 microfarad capacitor, which is decoupling. So there's no DC that can get into the in or out of the PicoDrone. The reason for the op amp is because of this resistor down here. This is 400k, it's quite a big resistor. So if this wasn't here, the output impedance of the whatever you plug this into would potentially affect the performance of the D2A. So this is kind of needed because this has an input impedance of a few megohms. Still not perfect, but at least it protects these kind of really big resistors from any kind of output impedance. So that's actually the circuit diagram of this stuff here. I think I missed a capacitor there. There's a 10 microfarads or something there. The last thing we need to do in order to bring this video home is to look at the delay looper. So here's the code. We've looked at the oscillators here, and the very last thing that we need to do is to get the value off to the D2A. So if we have no delay looper, then we're just going to D2A the signal total. Because we've still got some CPU cycles left, we can also add a delay. The way we add a delay is to use an array. Now, the PiPico has only got half a gigabyte of memory. It's got 512 megabytes of memory. So within that 512 megabytes of memory, we need to try and remember a value. I think I'm going to have to draw this so you can see how it works. Trusty notebook and Sharpie to the rescue. Imagine we have a tape. Actually, in our case, it's just going to be memory. Large chunk of memory. What we're going to do is write each point to a point in memory. But where we write it is going to be controlled by a variable called buffer point. Buffer point. And buffer point just increments. So every sample we just write into memory. When buffer point gets to here, which is the end of our memory, we set it back to 0. So by going from the maximum back to 0, we create almost an infinite loop, almost like a tape loop. So we're busy writing the data here. Then in order to create a delay, we can have a second point, which is we could call our read point. And the read point, if this is the buffer point, the read point is a certain amount behind delay, which is a value. So we then subtract to find the read point, or where we're essentially placing the read head. So this would be the record head. This is the read head on the tape. Will be this value, buffer point, minus delay. Delay, as you'll see in the example, is actually controlled by a knob. So we can change the location of the delay, how much we delay by. And in the Pico's case, I think the maximum memory we can manage is about 1 second. Here's the second version, where we actually have like a looper. So with the looper, we actually feed the value back in all the time and slightly decrement it. In fact, it goes down by half each time. And here the signal gains half of the value from the buffer every time. And the buffer is actually filled back up with the signal total. So you can see how the buffer is continuously getting stuff added to it and also getting half of what was in there before. So the signal is going to keep going round and round and round. once again, thank you very much for watching. That's going to conclude really the whole of the top row now for the PicoDrone. And what we'll see on the next episode is, because the Pico has 2 CPUs, we've basically covered the entire usage of one of the CPU cores. The rest of this is handled by the other core, and we'll have a look at this in more detail. Also, we're going to come back to the D2A, as there's a few more things to say about that. Okay, thank you very much, and I'll see you next time on the PicoDrone. There's also a little treat, PicoDrone treat, that I will be dropping out quite soon, with many thanks to Patrick Bartmus. So keep an eye out for that.